Something very strange keeps happening in evolution. Animals keep abandoning their limbs, not once, not twice, but over and over again in completely different branches of the tree of life. Animals independently become long, narrow, flexible, and unmistakably snake-like. In some lineages, legs shrink and disappear. In others, bodies simply elongate. Lizards do it, amphibians do it, and fish do it. Entirely separate lineages separated by tens of millions of years, arriving at the same, or almost the same, silhouette. And they're not closely related. They don't share a recent limbless ancestor. They're not copying one another. So what is going on? Why does evolution keep reinventing the snake body plan again and again and again? And what does that tell us about how evolution actually works? Once you start noticing this pattern, you really can't unsee it. If you live in Britain, for example, you may have encountered a slowworm, Anguis fragilis. At first glance, it looks exactly like a small snake. Smooth body, no visible legs, serpentine movement, but then it blinks. It has eyelids. It can drop its tail if threatened, something most snakes can't do, and genetically it isn't a snake at all. It's a lizard, more closely related to skinks and geckos than to any python or viper. Then there are amphisbaenians, often called worm lizards. They live underground in tropical and subtropical regions of the globe. Some have no limbs whatsoever, whereas others, like Bipes biparus, retain tiny front legs that look almost vestigial. They're quite cute as well, whilst completely lacking hind limbs. Their skulls are heavily reinforced, built for pushing through soil, and their bodies are ringed, segmented looking almost like an earthworm. They evolved this form completely independently from snakes. Now look at amphibians. Caecilians are limbless amphibians, closer to frogs and salamanders than to reptiles, and many species burrow through soil in tropical forests, completely limbless with reduced eyes and, once again, reinforced skulls. Sirens are another amphibian. They are elongated salamanders with tiny front limbs and no hind limbs. Amphiuma look almost identical to eels, but if you look closely, they retain tiny vestigial legs. They live in swamps and slow-moving water. None of these animals are snakes, yet they converge on the same elongated, limb-reduced body plan. And in fish, the pattern repeats again. Obviously, they were never tetrapods, so they didn't lose legs, but they did elongate. True eels, moray eels, knife fish, and even the electric eel, which isn't actually a true eel, but it converges the same elongated form. Different ancestry, different evolutionary histories, but same overall solution. This isn't a coincidence, it's convergent evolution. When different lineages encounter similar physical constraints, evolution often delivers similar mechanical solutions. So, the real question isn't why snakes, it's what makes this shape so effective. The snake body plan is not an evolutionary endpoint, it isn't a final stage of progress, it's just a tool. And like any tool, it is extremely effective at certain jobs. One of the most obvious is moving through confined spaces, so if your environment consists of soil tunnels, root systems, narrow crevices, dense leaf litter, or compact vegetation, limbs can actually become a liability. They snag on things, they require room to swing, they increase the width of your body, and they create drag. A long, narrow body can move forward with minimal cross-sectional resistance. You don't need wide tunnels, you don't need to excavate large cavities, you can move through spaces that would completely block a limbed animal. In burrowing lineages, this creates strong selective pressure, so what happens is limbs begin to shrink. Shorter limbs snag less, obviously, reduced limbs cost less to maintain, and eventually in some lineages they disappear entirely. But burrowing is not the whole story here. Limblessness also evolves in aquatic environments because water is dense, basically. Limbs create turbulence and drag, and a laterally flexible body allows for continuous undulatory propulsion, generating thrust along the entire length rather than from discrete paddles. True eels move by passing waves of muscular contraction from head to tail, for example, and that wave pushes against the water and produces forward motion. It's smooth, it's efficient, and in dense aquatic vegetation, narrow rock crevices, and reef systems, elongation provides access that bulky bodies simply can't achieve. Amphiuma and sirens inhabit swamps, wetlands, and submerged root systems, so their elongation is primarily not about digging, it's about navigating submerged obstacles in a dense medium. Obviously, soil and water share something important. They resist movement, and in both environments, a narrow, flexible body can be more advantageous than protruding limbs. But there's another context as well, and that is dense terrestrial vegetation. Some elongated lizards, like our friend the slowworm, live not underground but in thick grass and leaf litter. So instead of digging, they effectively swim through plant stems. A long body slips between vertical obstacles with minimal resistance. Limbs may still exist, but locomotion increasingly depends on axial bending rather than stride length. And then finally there is predation. A long, narrow predator can enter rodent burrows, it can pursue prey into rock crevices, it can hide in narrow cracks and ambush passing animals, and in snakes specifically, elongation interacts with feeding strategy. In effect, their skulls are highly kinetic, allowing enormous gape expansion, and they can swallow prey whole. Then a long body allows them to distribute that prey internally without severely compromising mobility. The snake-like form is not tied to a single ecological niche, it appears wherever environments reward continuous axial propulsion, narrow access, high flexibility, and situation where limbs simply provide diminishing returns. Hey, quick question, are you enjoying this video? If you are, please do consider liking, subscribing, and possibly even joining the channel, because Spirit and I really enjoy making these. Thank you very much. From a mechanical perspective, elongation has another major advantage. A typical mammal has roughly 30 vertebrae, whereas snakes can have often between 200 to 400, and that's hundreds of repeating structural units. Each one contributes a small degree of movement. Instead of relying on a few large limb joints, snakes rely on distributed flexibility. This allows incredibly small turning radii, it allows precise adjustments, and it allows locomotion in environments where large limb swings would simply be impossible. And here's something even more fascinating. In snake embryos, limb buds still begin to form. Early in development, the genetic pathways responsible for limbs activate, but then they're suppressed. The limbs do not fully develop, the genetic toolkit for legs hasn't been erased, it has just been modified. And fossil snakes like Najash retain functional hind limbs, so snake evolution was definitely gradual, step-by-step reduction, not instant loss. And similar limb reduction pathways have evolved independently in multiple lineages, not because they share a limbless destiny, but because their developmental biology makes it possible. Not every body plan can easily become limbless, of course. Lineages that already rely heavily on axial musculature and flexible rib cages are more predisposed to elongation. There are constraints. Evolution works with what already exists, basically. Now, what makes this even more interesting is that limb loss isn't just an ecological story, it's a developmental one. Vertebrate bodies are patterned early in embryonic development by genes that determine where structures form along the head-to-tail axis, and in many elongated lineages, what changes is not simply limbs disappear, but the balance between trunk identity and limb identity. In snakes, regions of the body that would normally form shoulder and pelvic girdles become absorbed into an extended rib-bearing trunk. The body becomes more torso and less appendage. That shift in patterning allows more vertebrae to form and reduces the anatomical distinction between regions. And this is important because you can't just remove limbs from any body plan and expect it to work. Humans, for example, it wouldn't go too well. The underlying developmental architecture has to allow elongation. Lineages that already rely heavily on axial musculature are more predisposed to successful limb reduction. In contrast, animals that rely extensively on limb-driven locomotion, like many mammals, face far greater constraints. That's one reason we don't see limbless mammals evolving repeatedly, even though some mammals do burrow. Developmental constraints shape what evolution can and cannot easily modify, and evolution does not start from scratch. It modifies existing blueprints, and in certain clades, that blueprint makes elongation a relatively accessible pathway. In others, it would require reorganizing the entire body plan, and that difference matters. There is also an energetic dimension, because, simply put, limbs are expensive. They require bone, muscle, nerves, blood supply, and coordination. They increase your surface area, they require maintenance, and if they stop providing significant survival advantage, then reducing them lowers energy expenditure. A modular spine scales efficiently, you can increase vertebral number without inventing an entirely new structure, and evolution tends to favour solutions that are both effective and economical in terms of energy use, that is. When a body plan is mechanically powerful and energetically efficient in a given context, it is more likely to evolve repeatedly. But none of this means a snake body plan is superior, it's just specialised. So in open terrain, limbs are extraordinarily useful. They allow sprinting, jumping, climbing vertically, manipulating objects, and if you look outside, you'll notice probably that birds dominate the skies with wings. Mammals dominate terrestrial niches with limbs, and insects dominate most of the planet with exoskeletons and jointed legs. Every body plan is pretty much a compromise. The snake form excels in certain environments and performs poorly in others. Evolution is not climbing towards an ideal, it is simply navigating trade-offs. Then there's a psychological reason this pattern feels so dramatic, and probably why we notice it. We don't usually say everything keeps evolving into frogs, but frog-like convergence happens. Snakes are visually extreme, simply put. They have a long body, no legs, no limbs, distinctive locomotion. Humans are neurologically primed to detect snake-like shapes. Across cultures, snakes trigger attention and vigilance. When we see an elongated and limbless animal, our brains immediately categorize it as snake-like. That makes the pattern feel uncanny, almost intentional, but it isn't intentional. It's constrained. Physics constrains movement, development constrains what is possible, energy budgets constrain what can be maintained. Given those constraints, certain shapes just become more likely. And the long, flexible, limbless body is one of those shapes. So when people say everything keeps evolving into snakes, what they're really observing is something deeper. When different lineages face similar mechanical and ecological pressures, evolution often finds similar solutions. Not because it loves snakes, not because there is a final form, even though that sounds kind of cool, but because there are only so many ways to move efficiently through dense mediums. Only so many shapes that minimize drag while maintaining flexibility, or maximizing flexibility, and only so many designs that balance access, energy cost, and survival. And the snake-like body just happens to be one of the most mechanically elegant solutions evolution has ever discovered. Again, and again, and again. And honestly, that's kind of incredible.